Hello, in this lecture I will explain what is mathematical induction. Mathematical induction is a logical method to prove that a statement or an equation or a claim is true for all the natural numbers. A natural number is a positive number, and that is also integer, like 1, 2, 3, 4, etc. So we have two stages in mathematical induction. The first stage is we must check that the statement is true for n that equals to 1, and if it is indeed true for n that equals to 1, then we will go to the second stage, that is to assume that the statement is true for n, and then to prove it for n plus 1. So in this way we will create two expressions. The first expression is the induction hypothesis, or the induction's assumption. We assume that the statement is true for n. So that is the induction's hypothesis, and we rely on this expression in order to prove that the statement is also true for n plus 1. Okay, and after we proved that the statement is true for n plus 1, we actually proved that the statement is true for all natural numbers. And I will explain why. Because we should remember that in the first stage we checked that the statement is true for n that equals to 1. So we verified that the statement is true for n that equals to 1. And then in the second stage we proved generally that if it is true for n, it must be true for n plus 1. So we can say that we actually have already proved that it is true for n that equals to 1, and from our general proof we can say that it also true for n plus 1. That is to say, n equals to 1, so it is true for 1 plus 1. That is to say, it is true for 2. And then we will repeat on the same process again. Now that we know that it is true for 2, we can again rely on our general statement that says that if it is true for n, it must be true for n plus 1. We can deduce that if it is true for 2, it must be true for 2 plus 1. That is to say, it is true for 3. And because of the fact that it is true for 3, it must be true for 3 plus 1, according to our general proof. That if it is true for n, it must be true for n plus 1. So it is true also for 4. And because of the fact that it is true for 4, it must be true for 4 plus 1, that is 5. And so on and so on. And in this way, we actually proved that the statement is true for all natural numbers. Okay, so in order to clarify the topic, I will give you two examples. The first example is actually uh, uh, 1 plus 2 plus 3 plus n equals to n times n plus 1 divided by 2. So we must prove this statement or equation or claim for all the natural numbers. That is to say for 1, 2, 3, 4, etc. Okay, so the first step so I will show you the statement of the equation. It is 1 plus 2 plus 3 plus 4 plus 5 plus n equals to n times n plus 1 divided by 2. So we must prove this statement for all natural numbers. So the first step that we will do is the first stage is to check if the statement true for n that equals to 1. Okay, this is stage 1. We will check if the statement true for n that equals to 1. So in the right side of the equation we have 1 because n equals to 1 equals to n times n plus 1 divided by 2. It is 1 times 1 plus 1 divided by 2 equals to 1 times 1 plus 1, yes, mistakenly not root 2, so I will fix it. So 1 times 1 plus 1 is 1 times 2 divided by 2. 1 times 2 is 2 divided by 2 is 1, so 1 equals to 1. So we actually passed the first stage. We checked that this statement is true for n that equals to 1. We found out that we have here in the right side of the equation 1 equals to n times n plus 1 is 1 times 1 plus 1 because n equals to 1. So it is 1 times 1 plus 1 divided by 2 equals to 1 times 1 plus 1 is 2, so it is 1 times 2 divided by 2. 1 times 2 is 2, 2 divided by 2 is 1, so 1 is equals to 1. So we passed the test, and we actually verified that this statement is true for n that equals to 1. So now we can go to the second stage. That is to say, we will create now two expressions. In the first expression, we will assume that this statement is true for n, and then in the first expression we will prove it that is true for n plus 1 when as we rely on the assumption that is true for n. So the first expression will be for n. It actually, we assume that the expression is true for n. So it is 1 plus 2 plus 3 plus n equals to n times n plus 1 divided by 2. So this is actually expression 1 is the induction's hypothesis. Okay, inductions. Hypothesis. So we assume, induction hypothesis is that we assume that the expression, this expression is true for n. That is to say 1 plus 2 plus 3 plus n equals to n times n plus 1 divided by 2. So this is our assumption, that the statement is true for n, and we will rely on this assumption in order to prove that this statement is true also for n plus 1. So we will have to prove that this statement is true for n plus 1. So we will create now the statement for n plus 1, and we will prove that this statement is true for n plus 1. So the expression for n plus 1 is 1 plus 2 plus 3 plus n plus n plus 1, because we must prove that this statement is true for n plus 1. So we will go until n plus 1 is equals, and here in the left side of the equation we have n plus 1 divided by 2, but we have to prove the statement for n plus 1. So wherever it is written n, we will write n plus 1, because we have to prove this statement for n plus 1. So n plus 1 will become, n will become n plus 1. So wherever is written n, we will write n plus 1. So it is, here is written n, so we'll write n plus 1 times n plus 1. So here we will write n plus 1 instead of n, and plus 1. Okay, so it is n plus 1 plus 1, all divided by 2. So expression 2 is expression for this expression for n plus 1. Okay, and we must prove expression 2 for n plus 1. So we will rely on our assumption that expression 1 is true in order to prove expression 2. Okay, so actually we should look on this expression. The expression in the green color. We know, according to our expression, according to our assumption, that this expression equals to n times n plus 1 divided by 2. So actually we can replace this expression by n times n plus 1 divided by 2, because according to our assumption this statement is true for n, yes? So we can replace or substitute this expression by n times n plus 1 divided by 2, because according to our assumption there are two expressions that are equal to each other. So we'll substitute it by n times n plus 1 divided by 2. And here we have n plus 1, so we will copy it as it is. And all equals to n plus 1 times n plus 1 plus 1 is n plus 2, all divided by 2. So actually we substituted the expression in the green color by this expression, because according to our assumption they are equal to each other. And then here it's written n plus 1, so we copy it here, all equals to n plus 1 times n plus 2 divided by 2. Okay, so we must prove that expression 2 is true. So actually we can divide the two sides of the equation by n plus 1, because we have n plus 1 in both sides of the equation. So we can divide it by n plus 1, because n plus 1 will never be 0, because n is natural numbers, not one number. So we can divide it by n plus 1, both sides of the equation. N times n plus 1 divided by 2 divided by n plus 1 is n divided by 2, plus n plus 1 divided by n plus 1 is 1, equals to n plus 1 times n plus 2 divided by n plus 2 is n plus 2 divided by 2. So here, as you can see, n times n plus 1 divided by 2 divided by n plus 1 is n divided by 2, and n plus 1 divided by n plus 1 is 1, all equals to n plus 1 times n plus 2 divided by 2 divided by n plus 1 is equals to n plus 2 divided by 2. Okay, and this is the second expression that we must prove. Now we can separate n plus 2 to two parts, so it is actually the second expression that equals to n divided by 2 plus 1 equals to n divided by 2 plus 2 divided by 2 equals to n divided by 2 plus 1 equals to n divided by 2 plus 1. So here we separated n plus 2 to two parts. It is n divided by 2 plus 2 divided by 2. And here it is the same. It didn't change anything. So here it is n divided by 2 plus 2 divided by 2 is 1. So it is n divided by 2 plus 1 equals to n divided by 2 plus 1. So we actually proved that expression 2 for n plus 1 is correct. So we actually proved that this statement is true for n plus 1. We assumed that this expression is true for n, and according to this assumption we proved it for n plus 1. Here we proved it for n plus 1. We assumed that the expression is true for n, that is the first expression, and we proved that this expression true is for n plus 1. So in this way, actually, we proved that this expression is true for all the natural numbers, because we actually, in the first stage, we checked that this expression is true for n that equals to 1, and then in the second stage, we proved that if it is true for n, it must be true also for n plus 1. Okay? So in this way, we know that this expression is true for n that equals to 1 because we checked that it is true. And according to our general proof, we proved that if it is true for n, it must be true for n plus 1. So we know that it is true for n that equals to 1. So according to our general proof, it must be also true for n plus 1. That is to say, for 1 plus 1. So it is true for 1 plus 1 that equals to 2. And now we will do the same process again. We will repeat on the same process again. We know that this statement is true for n that equals to 2, and according to our general proof, it must be true for also 2 plus 1, that is n plus 1, because n equals to 2. So it is also true for 3, and because of the fact that it's true for n that equals to 3, it must be true also for n plus 1, according to our general expression. And n plus 1 is 3 plus 1, that equals to 4. And because it is true for 4, it must be true for 5. And because it is true for 5, it must be true for 6. So we always repeat on the same process, and in this way we actually proved that this statement or this claim or equation is true for all the natural numbers. Okay, so now I will give you another example to clarify the topic. The second example will be 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n to n square plus to n square times n plus 1 square, all divided by 2. Okay, so the statement that we must prove, okay, write it again. So the statement that we must prove, for all the natural numbers is actually 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n squared times n plus 1 squared divided by 4. So the first step that we will do is actually we will check that this statement is true for n that equals to 1. So here in the right side of the equation we will have n equals to 1, so it is 1 to the power of 3, and in the this is in the left side, in the right side of the equation, and here in the left side of the equation we have n to the power n squared times n plus 1 square all divided by 4. So it is n equals to 1, so n square is 1 square times 1 plus 1 square all divided by 4. So it is actually 1 square is 1, 1 plus 1 is 2, so it is 1 square times 2 to the power of 2 all divided by 4. It is equals to 1 to the power of 2 is 1, and 2 to the power of 2 is 4, and all divided by 4 equals to 1 to the power, 1 times 4 is 4, all divided by 4 is 4, and 4 divided by 4 is 1, so we have 1 that equals to 1. Okay? So we passed the first stage, and we actually verified that this statement is true for n that equals to 1. Okay? Now we will move to the second stage. We will assume that this statement is true for n. That will be the induction hypothesis, and according to this assumption So that will be the first expression, and according to this assumption we will prove that this statement is true for n plus 1. Indeed, it will be our first expression, and we must prove, and we will prove the second expression as we rely on our assumption, on our inductions hypothesis, or on our first expression. Okay, so first of all we will create our inductions hypothesis. That is to say, we will assume that this expression is true for n. So n 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n squared times n plus 1 squared, all divided by 4. So our inductions hypothesis will be that actually this statement is true for n. That is to say, 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n squared times n plus 1 squared, all divided by 4. So this is the inductions hypothesis, so inductions assumption, and as we rely on this assumption we will prove that this statement is true for n plus 1. That is to say, now we will create the second expression for n plus 1. So 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 plus n plus 1 to the power of 3, because we must prove that this expression is true for n plus 1. So we will continue from 1 until n plus 1. Okay, so all n plus 1 to the power of 3 equals, here in the left side of the equation, wherever it is written n, we will write n plus 1, because we want to prove this statement for n plus 1. So n will become n plus 1. So here it's written n squared, so it will become n plus 1 squared. And here it is n plus 1 squared, so it will be n plus 1 plus 1, because n becomes n plus 1. So it will be n plus 1 plus 1 square, all divided by 4. So the expression that we must prove is for n plus 1. This expression for n plus 1, it is 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 plus n plus 1 to the power of 3. equals to, wherever it is written n, we will write n plus 1. So it will be, instead of n squared, it will be n plus 1 squared times n plus 1, it will become n plus 1 square, all divided by 4. So we must prove that the second expression is true, and as I already told you, we will rely on the second expression in order to prove that and we will rely on the first expression in order to prove that the second expression is true. Because we assume that the first expression is true. So if we look on the second expression, on this part of the expression, this part of the expression actually equals, it is the same, yes? This is the same as this. So this equals to n squared times n plus 1 squared divided by 4. So we can substitute the expression in the red color by n squared times n plus 1 squared divided by 4, because according to our assumption they equal to each other. This is the same as this, and this equals to this. So this equals to this, so we can substitute the expression in the green color by n squared times n plus 1 squared divided by 4. So we will do it now. So the second expression will be n squared times n plus 1 square, all divided by 4. So, as I have already told you, we substitute this expression by n squared times n plus 1 squared divided by 4, because they equal to each other. And we have in the second expression also n plus 1 to the power of 3, so we will leave it as it is. We will copy it, n plus 1 to the power of 3 equals to n plus 1 square, and n plus 1 is n, it is n plus 2, so it is n plus 2 square, all divided by 4. Okay, so this is the expression that we must prove, and we actually substituted the expression in the green color by n squared times n plus 1 squared divided by 4, because according to our assumption they are equal to each other according to the first expression. And then we have plus n plus 1 to the power of 3, so we copy it here, and all equals to n plus 1 times n plus 1 is n plus 2, so it is n plus 2 square, all divided by 4. Okay, so we must prove that the second expression is true. And what we will do is actually we will divide both sides of the equation by n plus 1 square. Okay. So what we left is n squared divided by 4 plus n plus 1 equals to n plus 2 square divided by 4. So after we divide both sides of the equation by n plus 1 square, so n square times n plus 1 square divided by 4 divided by n plus 1 square is n square divided by 4, and n plus 1 to the power of 3 divided by n plus 1 square is n plus 1, and n plus 1 square times n plus 2 square divided by 4 all divided by n plus 1 square, it is n plus 2 square divided by 4. Okay, now we will multiply both sides of the equation by 4, so it will be n squared divided by 4 times 4, it will be n squared plus n plus 4 times 4 is n 4n plus 1, and n plus 2 square divided by 4 times 4 is n plus 2 square. Okay, so we multiply both sides of the equation by 4, and n squared divided by 4 times 4 is n squared, n plus 1 in brackets times 4 is 4n plus 1, and n plus 2 square divided by 4 times 4, it is n plus 2 square. Now we will open the brackets. So here we open the brackets, n squared plus 4 times n is 4n, and 4 times 1 is 4, all equals to n plus 2 square, according to the rule that a plus b square equals to a square plus 2ab plus b square. We can say that n plus 2 square, it is n square plus 2ab is 2n times 2 is 4n plus b square, it is 2 square, it is plus 4. So we have an identity. So in this way we actually proved that this statement is true for n plus 1. So we actually assumed that this expression is true for n, and according to our assumption we succeeded to prove that this statement is must be true. If it is true for n, it must be true for n plus 1. And in this way we actually proved that this statement is true for all natural numbers, because we checked that this statement is true for n plus 1, and because of the fact that it is true for n plus 1, it must be true for, because of the fact that it's true for n plus 1, it must be true for 2, because of our proof that if it is true for n, it must be true for n plus 1. It is true for 1, and n equals to 1, so it must be true for 1 plus 1, that is 2. So we know that it is true for 2, it must be also true for 2 plus 1, because of our general expression, because of our general proof that if it is true for n, it must be true for n plus 1. So we know that it is true for n equals to 2, it must be true for n plus 1, that is to say it is true for 3. And as we know that it is true for n that equals to 3, it must be true for n plus 1, according to our general proof. So it must be true for 3 plus 1, that is to say for 4. And we will repeat on this process again and again. And in this way, actually, we proved that this statement is true for all the natural numbers. Okay? Thank you very much.